We're going to look at a couple of examples for evaluating limits algebraically. The first example is the limit as x approaches 8 of x cubed minus 64x on the numerator divided by x minus 8. If we were to plug 8 directly into this function, we would have a 0 over 0 scenario, which is an indeterminate form. If we actually look at factoring the numerator, we can factor in a greatest common factor of x, and we still have to factor it further because we have a difference of squares. And we get x minus 8, x plus 8 times by x on the numerator, and on the denominator we have x minus 8. The x minus 8 will cancel out, and now we're left with something that we can actually evaluate the limit as x approaches 8. When we plug 8 into the equation, we get 8 times 16, so we will get 128 for our limit as x approaches 8. Another example is the limit as x approaches negative 2 of 2x plus 4 divided by 12 minus 3x squared. This one again, if we plug in negative 2 into the numerator and the denominator, we're going to get a 0 divided by 0 scenario. Again, it's indeterminate. So in this particular case, we can actually factor both the numerator and the denominator in this case. There's a greatest common factor of 2 in the numerator and a greatest common factor of 3 in the denominator. The denominator can still be factored further because now you have a difference of squares. 2 minus x, 2 plus x. Now in this particular case, x plus 2, 2 plus x, those are the same thing. If it was the case where it was x minus 2, you'd probably want to look at this one and factor out a negative 3 if that was the case. So do watch your signs. Now we have something that as we plug in negative 2, we have 2 over 3, 2 minus x. We don't have division by a negative or by a 0 anymore because when we plug in negative 2, you get 4 at the denominator. So as a result, your limit ends up being 2 over 12, which reduces down to 1 over 6. Another format you may see is where you see radicals in either the numerator or the denominator, or in this case both. One technique in solving this one, again, it is an indeterminate form because if you do plug in 4 and 4, 5 minus 4 is 1, square root of 1 is 1, 1 minus 1 is 0, 2 minus the square root of 4 is 2 minus 2, which becomes 0. So it is an indeterminate form, but we can use multiplying by the conjugate. In this particular case, we're going to set this up. We can do it either in 2 steps or you can do it in 1 step. So the first thing I'm going to do is multiply by the conjugate of the denominator, to top and bottom. Now this will help eliminate the radical in the denominator, and we will get I'm going to leave the numerator in factored form and only worry about the denominator. In this case now I have 4 minus x. Now you'll notice that if I plug 4 into this right now, it's still going to leave me a 0 on the denominator. So we're going to multiply by the conjugate of the numerator and see if that helps us. Now if I look at just the numerator and I look at the 2 conjugates, this guy or this guy with this conjugate, when I multiply that out, I'm going to get 5 minus x minus 1. And I'm going to keep 2 plus root x here, and I'm going to keep everything else on the denominator in factored form for now. what we just multiplied when we multiplied the two conjugates now reduces down to 4 minus x. So these two actually cancel out. Now it looks very similar to what we started with. The difference is we now have the signs of the two conjugates rather than subtraction. So if we were now to plug in 4 into our new limit, x approaches 4, 2 plus root x, all over the square root of 5 minus x plus 1. And we plug 4 into everything. Now we have 2 plus the square root of 4, which is not 0. We have 5 minus 4, which is still 1, but we have now plus 1. So we end up getting 2 plus 2, which is 4, all over 1 plus 1, which is 2, which gives us 2. Another example involves fractions and making things into one entire fraction rather than partials. In this particular case, if I again was to plug in -4 into the numerator and into the denominator, if I plug -4 in here, 1/4 plus -1/4 becomes 0. And if I plug in -4 here, 4 plus -4 becomes 0. Again, I'm in an indeterminate form. To work with this one, you'll want to make sure that you put it into one entire fraction. In order to do that, first we're going to work with our numerator. These two fractions, we need to find a common denominator. The common denominator is going to be 4x. One side I needed to multiply by x, and one side I needed to multiply by 4. Now when you have a fraction over a fraction, it's the same thing as, you can write it as a over b divided by c, which is then the same thing as a over b multiplied by reciprocal. So we can rewrite this as the limit as x approaches -4 of x plus 4 all over 4x divided by 4 plus x, which is the same thing as then multiplying by 1 over 4 plus x. There we go. You can now see that this cancels out quite nicely, and then we are left with just the limit as x approaches -4 of 1 over 4x, which we can evaluate to be 1 over -16. Another indeterminate form is when we have the limit of two fractions and both fractions are approaching infinity. In this particular case, when we plug in 0 for x, we actually get a case of infinity minus infinity, which falls into the indiscriminate form. What we are going to do is look at how to make these two fractions into one complete fraction. So in this particular case, we're going to say the limit as x approaches to 0 of 1 over x minus, and if we put this in factored form, we can see that all we need to do is multiply one of the fractions by x plus 1. If we multiply the first fraction by x plus 1, we get x plus 1 so we get this. And when we can join the two fractions, we can see that the plus 1 subtracting the minus 1, we're just going to have x on our numerator. We still need to cancel something out, and we can see that they have a factor of x on both numerator and the denominator. So we can write it as the limit of x approaching 0 of 1 over x plus 1, of which we can now evaluate. If we plug 0 in, we now get the limit is going to be equal to 1.